Okay, in this lecture, we're going to talk about finding whether the inverse of a continuous function is continuous. And we're going to be taking care, and it's going to be a bit tedious, but it's short. Okay. We're going to start out with some definitions, and again, we're being very careful with language. Let f from a to r be a function. We say that f is increasing if for x1 and x2 element of a, x1 less than x2 implies f of x1 is less than or equal to f of x2. We say that f is strictly increasing if x1 less than x2 implies f of x1 is less than f of x2. The terms decreasing and strictly decreasing are defined analogously. Okay. We say that f is monotone if it is an increasing function or a decreasing function. We say it's strictly monotone if it is a strictly increasing function or a strictly decreasing function. It is left as an exercise to the reader to show that strictly monotone functions are invertible and their inverses are strictly monotone. So there are your definitions. Okay, so this result is technical, but it is important. We're going to use it to prove important results, and so we're going to take our time with it. Okay, that's why we have 5 slides and a whole video devoted to just the 5 slides. So the theorem is this: let I be an open interval, and suppose that f from I to r is a continuous function, that it's strictly monotone as well. Let j be equal to f of I. Okay, so j is the image of I. And let g be a function from j to r. Let g be the inverse of f. Then, okay, all of that stuff going on, then g is continuous. Okay. So to simplify this, which is going to be complicated enough, to simplify it, we're just going to work with f as a strictly increasing function. All the techniques will go over to f, a strictly decreasing function as well. I'm going to start out again. This is a theorem. Okay, what is it? It's about proving that g is continuous. So I'm going to prove that g is continuous at every point in its domain. So let's just pick a point in its domain. Why not an element of j? And I'm going to say let x naught be equal to g of y naught. And so we will show that g is continuous at y naught. Okay, so this is about proving that g is continuous at y naught. All right, so since we're proving g is continuous at y naught, we'll start out with let epsilon greater than 0 be given. Okay, and so we're just assuming, it's a small number. It will not hurt us to assume that epsilon is small enough so that x naught minus epsilon, x naught plus epsilon is contained in I, right? We can just, since I is open, we can just squeeze it in there so that it fits. Okay, so since f is a strictly increasing function, we can say that f of x naught minus epsilon is less than y naught, and f which is less than f of x naught plus epsilon. Let's do a picture. So what I have here, my function f, I have graphed here in red. Okay, my point y naught, it's in the domain of g, but the domain of g is the range of f, so I've got it over here on my vertical axis. My g of y naught is down here, it's my x naught. I have my x naught minus epsilon, my x naught plus epsilon, and my function f then will map f naught minus epsilon up to here, my x naught back to y naught exactly as it should, and my x naught minus x naught plus epsilon to f of x naught plus epsilon. And so again, since it's a strictly increasing function, we have them all lying in a row right there. Now, since f is continuous, it follows by the mean value theorem that this closed interval f of x minus epsilon to f of x naught plus epsilon is contained in J, which is that every point between these 2 points will stay in that interval, in that set J. All right, so let's look at the picture there just to see what I'm talking about. So from this point here to this point here will be contained in the set J, and it's visually obvious, but we need to have the statement use of the intermediate value theorem because pictures can deceive. All right, so we have that interval contained in J now. So what we're going to do is we're going to y naught might not be exactly centered in this interval. If you remember the picture, it wasn't. So what we're going to do is let delta be the smaller of the two distances that y naught is from the endpoints of the interval. Okay, and so delta is greater than 0, and so we have now that this y naught minus delta to y naught plus delta, it is contained in this interval from f of x naught minus epsilon to f of x naught plus epsilon, and that is contained in J. Okay, so we have this inequality just flowing through so that this smaller interval will be contained in J. And so we just accidentally proved that J is open, by the way. Therefore, okay, we have that this y naught minus, that f of x naught minus epsilon is less than or equal to y naught minus delta is less than y naught plus delta is less than f of x naught plus epsilon. So let's look at that picture again. So in this picture, what I'm doing, I'll choose my delta to be this value right here because it's the smallest of the two distances. And so I would have my y naught minus delta down here, my y naught plus delta down here. So I have this little open interval around y naught. And notice that as this function's drawn here, my g is going to map it back so that it will be inside this. Okay. But again, pictures can be deceiving. Let's look at how the proof is set up. Okay, so all right, last slide. So since f is strictly increasing and g is the inverse of f, it follows that g is strictly increasing. And so I can apply g to this inequality, and it preserves the order on it. And so therefore I have g of f, they undo each other, and so I have x naught minus epsilon is less than g of y minus delta is less than g of y naught plus delta is less than x naught plus epsilon. So if y is between is this interval, then g of y is between the two endpoints of this interval. Therefore, we have that the absolute value of y minus y naught is less than delta, that it implies that g of y minus g of y naught in absolute value is less than epsilon, and so g is continuous at y naught.